Good morning, fellow travelers. Anyway, no one's trapped, no one's showing. Hi. So today is going to be a rather short workshop. Befitting because for the past two workshops we've been overtime for like roughly half an hour sometimes. All right. So today we're talking about the distance sensor here. In particular, we will be talking about. Oh, it's not shared. Okay.
It's shared.
Sorry, I mean it's not going to the HCSR04. So this is an ultrasonic distance sensor. And the way it works, it's sort of similar to how bats move when they make noises. That makes sense. Because I'll explain that later. It provides a 2 centimeter to 400 centimeter non-contact measurement function. As is with any distance sensor, it's probably going to be non-contact most of the time anyway. And has a ranging accuracy that's up to 3 millimeters. Okay. So this model, the model that we have here, the HC-SR04, includes an ultrasonic transmitter, receiver, and a control circuit, right? The transmitter is the one that initially sends a signal out, right? In the pulses, in 8-burst pulses, and then receiver is the one that receives it. The duration in between is really useful to determine the time. To determine the distance. Okay, so the principles of operation, as I just explained here, is you need to have an I/O trigger of at least 10 microseconds, high level. This is all from the data sheet, and the data sheet itself is on the resources folder, right? So then the module also sends 840 kilohertz burst, so it goes like that, right? It detects whether there's a pulse or signal, and in class, at least in the classes I've been, which is only one class I've used this. You actually use an IR distance sensor. So to use that, you have to configure the ADC module on the TIVA-C, which is what I was doing before I realized, well, I can't really use that because my guy over here is not actually, he doesn't use any voltages to do it. Okay, so let me show you that on the screen. So this is the timing diagram of the HCSR04, the distance sensor. This is also from the data sheet. What you see here is what I was talking about earlier, where you need a trigger input of 10 microseconds at least, and that it actually works in like sonic bursts. So it bursts out 8 cycles, and that sort of reflects. It hits something and it comes back to the echo pin, and then the distance there is determined that way. So let's go here, how to use. Essentially, what we're really going to be doing is we're going to be finding the T2 minus T1, the delta time, and then dividing that by 58 or 148 to get it in centimeters or inches. So and this function, by the way, this formula is not like it's on the data sheet as well, and it's actually pretty reliable, I would say. Also, I mean, the accuracy you would also have to work out as you go with the project. But if you compare it to an IR sensor, this is probably the best way to go. It's also really easy to use, and that's why I'm going to show you. And another IDE is called Energia IDE. It's similar to the Arduino IDE, and the best part about this is you don't really have to even install anything. Well, I mean, you do have to install the installer, of course, but like you don't actually have to do any extra thing by like allow all of that. It actually just comes prepackaged, a free downloaded from the Energia thing, and it's actually also a TI software. So Energia falls under the category of non-advanced, I would say, at least from what the TIVA-C packaging shows, right? So this is the pin map that you would find on the website for Energia. And the thing to really pay attention here, I would say, is that all of the pins, you go from 1 to 40, right? So each one of the pins in, like, let's say if you use in Keel or Code Composer Studio, you would have to say PV5, PV0, etc. Over here, you can just use 1, 2, 3. And because each one of them is unique, we're fine. Today, the pins we're going to be using is pins, where is it? Pins PC4 and PC5. And those are pin numbers 37 and 36, which is right here. Okay. And they fall rightly here on the TIVA board and also on the back. So now we'll just go back into the code because it's really fairly simple code. And also, this is also my recommendation, right? Is if you're using for a DIY project with the TIVAs, you might just want to use them like an Arduino, which means just use the IDE and Energia, because the setup is easy and like it's very user friendly. As opposed to using Keel and Code Composer Studio or other form of IDE, because those are not user friendly, and of course you have to go through a lot of configurations. Here you don't really have to do much. All right, so let me stop this share real quick. All right, give me a moment. I'll open Energia and then go from there. Actually, I'm going to show them what I mean. Hold on. All right, so I'm actually going to show you what I sort of mean when I say it's easier to use. So this is something that I downloaded yesterday from the website, right? It comes in as zipped. All you have to do is extract. It's here. And you go inside this folder and you literally just run this. And you have it. And all of the drivers do come. And if you have Code Composer Studio installed in your thing, in your machine, and you have the drivers, then you don't even have to worry about all of the drivers because they're already there for you. And the moment you connect your TIVA, right, what you will see, can they see this screen, man? Can they see my
No.
They cannot. Okay. Yes. I only showed you the downloads. Mine. Okay. So now we're in the Energia screen. As again, after you click that .exe file, it just shows up. This is literally your entire programming window. And if you go to tools, look at the board, it automatically connects to your specific board. Now, if you don't have Code Composer Studio with all the drivers, of course you will have to download the TIVA-C libraries. But they're also easy to find. It's all in the Energia TI. Just Google TI Energia, or you don't even have to Google TI. Just Google Energia, ENERGIA IDE, and then it's like literally the first link. Okay, so this is my board. We have it collected. I'm actually on port COM6 because that's is from debugging yesterday that I found out that this works. All right, so I'm just gonna go into code mode now. So I'll show you what to do. Let me double check something real quick. Ooh. All right, back from the break. Also, oh yeah, another thing, I'll just go over what the void setup and void loop means. So in this code setup, at least in this IDE, you don't really have main function like you do have in Qt or Code Composer. What you do have is you have this setup function, you have this loop function, right? In this setup function, you have, as it says, you literally just put your configuration code. So the configuration that you would probably do in Code Composer, you would just put it here because it runs the code once. Inside here is like an infinite loop, so you don't really need to while loop it. It just you just put that code there, and it will rerun. It will actually keep on running over and over and over and over again until you basically stop the TIVA-C. And actually, not even that. Yeah, when you stop the TIVA-C, because even if you close this application, after you have uploaded the code to the board will keep on running it. Okay. And so let's go back to coding. Yeah, I'm actually going to define some pins here. So we have, as I showed on the PowerPoint, we have echo and trigger pins on the HCSO4. That's the pins we have to worry about. Of course, there's ground and VCC, right? And I mean, I know you can't sort of see. Oh, here. So right now you can see like it's connected to the TIVA-C.
Oh, did you want to show that part?
I was just going to show them why I have it connected to.
Okay. Let me just co-host because then it focuses on.
Oh, okay. Cool. Yeah, I just want to show the wires.
Okay, now you can show.
Okay, let me go here. So the reason right here, you can see it. I have a battery pack that provides 5 volts. Ooh. Yeah, sorry, I'm not a good cameraman. Just an engineer. Anyway, we have an external VCC source because there's a VCC pin here on here. Ooh, right there somewhere, right here. And the TIVA-C by itself cannot provide 5 volts. It only provides 3.3 volts, which isn't good enough for this. So that's why I have to use an external battery pack. And then the thing I notice is this wire is the ground wire, right? And this ground has to be for the TIVA-C board. I mean, because you have to ground it with respect to the board. If you don't do that, it actually will not work, right? And this is the echo pin, and this is the trigger pin, and this is the echo pin that's connected right to the yellow and white wires, respectively. That's it. Thank you, Matt. Okay, close. So, gracias. All right. All right, thank you. Share. All right, so that's what I'm going to do here. I am going to define a few pins. And the reason I am doing this is because it's easier for us to later go ahead and change the pins from the code, right? As opposed to going inside the function and changing. It's much easier. It's basically in the terms of modularizing the code. I don't know what happens, but when I come inside in front of this camera, my tongue just gets stuck. But that's not how I usually talk. Anyway, that's the whole thing. It's also what you would do in industry too. Like you will not just go ahead and use specific pins inside of functions. You'll have it somewhere else, and you do it from that macro, because it's easier to change code later, right? Because right now we're only writing one little small thing. Imagine you had like a huge file with a whole bunch of code for a complex robot. You're not going to have specific pins inside because then it's a nightmare to change. So when you code for yourself, you should also just have this practice where you make it better for yourself. And I'm saying that from experience because, I've been there, done that. So, and you will be surprised how easy it is to code well. So now let's go to setup pin. And in here, all we have to really set up is we have to set up both the echo pin and the trigger pin as input and output. Literally, that's it. And also, this one was PC4. So P stands for port, C is for the base, and 4 is the pin number, right? So port C5. And this pin map with the numbers only, I also have on the PowerPoint that is on the GitHub. So you're good there. And if you want to know where that came from, it came from the Energia website. And the reason is there, it's because, again, it's a TI software. And you can see from the logo there too, right? Like it's a rocket, which is also on the TIVA-C. So it's not something that is not part of the TI family. So here we do pin mode. And we're just setting the mode of the pin. And if you look at the data sheet, it's called direction, DIR. So in Keel, you would go something like DIR, register something. And you have other APIs here. So we do echo. We do, we'll go trig pin first, because that's the first pin we wrote. Trig pin, PC4. Trig pin, and then comma. The trigger pin is the output. And the reason why that's output is because it's the one that sends this first burst of sonic waves out, right? So echo is the one that receives it. So it's the output like that. Okay. And then pin mode, right? Echo pin. This is the input pin. This is the one that listens for all the sonic wave. And that in policy, you're done here. So if you were using LEDs and whatnot, you would also basically come here and just do it. But we're not doing that. That's fine. Oh, and then lastly, we have to do something called serial dot begin 9,600. So this It's similar to UART. So it's basically that's what that is. Our TIVA-C supports serial communication, right? It supports UART, I squared C, and and there's something else. I forget it. I forget it. In any case, when you have this IDE, you get to just sort of simulate that. So that's why I'm on COM6, right? When I was working on this yesterday, it the actual code started the outputs were printed, sorry, on COM6. If you were using a Bluetooth module or something with and then you were connected via UART, you would also have something similar to this, except you will not do serial.begin, you'll do something specific to the board in the data sheet. That 9600 is just the baud rate. We can change the baud rate later. You can actually change it to whatever you want it to be. It's just you have to like, let me open the port. Okay, so when I open the port monitor, yeah, this is from previous. So this is what the code will look like. The code doesn't run right now. The code is already in my board. That's why. If you change the baud rate here, 9600, you can change it to any one of these values, right? So if I go here now, there's nothing. It actually shows up here too, but that's not because I of my code. That's because it's already printing. But in any case, let me close that. Let me upload this code to my board right now. Oh, I have to save this somewhere first. Hold on. I also usually don't work with the software either. So I was planning to do this in Code Composer. It was just like had it off configured, and then it was like, oh wait, I can't use ADC. So that was my bad. Test file 2.0. 2. Okay, let me say that. So that was my bad. Oh yeah, no, I'll also say. So the verify here is for the compiler. Okay. So if you click on the check mark, it just compiles it. If you upload, that's the one to upload and execute the code. So it's very similar to the Arduino IDE, actually. And all of these functions, you'll actually find that for Arduino too. And you don't worry about that, right? That does, I don't even know what that means. Like Google, it doesn't really mean much. You just need to see that. And let me try to open tools real quick. And also, oh, actually, it's already open. Okay. Wait, there's the issue. Hold on. Oh, actually, never mind. I think I closed the phone. That's my bad. I'm being stupid. I closed the serial monitor. Are you able to see the serial monitor?
Yeah.
Are you able to see the serial monitor?
It showed up for like a second. Now it's not showing up.
Okay, well that's fine because what I was just trying to show was that after I uploaded the code, the serial monitor, there's nothing in there. There's actually nothing in there right now.
Okay.
But it'll come up again after we finish coding. So let me finish the code here, and then we'll go back to showing it. Okay, cool. All right. So I'm gonna do serial.print. Actually, not even that. So let's go double, because the distance is going to be in some decimal form after you divide, right? Double distance. I just call dist. You have int duration. For duration, I'll call dur. The duration is gonna be the duration of the period. So it's like your, like it's on the PowerPoint. The two little peaks, right? We just want the distance in the middle. You looked at me like you didn't know.
No.
It's just the way. It's just you want the T2 minus T1 and then divide. So now we're going to write to the trig pin first. Digital, right? Trig pin. And the reason it's a digital write is because it's a digital signal. Okay, it's an EM wave, so it's digital. And low first because we want to make sure it's off. And then delay microseconds. So over here you can delay to however many microseconds you wish. Just make sure that you account for that in your measurements. But usually it's 2 microseconds here. I can make it 5. That's perfectly fine. It's just the delay is only there so that the microprocessor can actually output a low signal first, so that it's actually low, and then when you do make it to high, there's enough gap that a high can be seen. So 2 to 3 or even 5 microseconds, that's good enough. Let me just put 5 microseconds here and go here now. Now we go digital right. Yeah, digital right. Okay, now we want to write a high. Okay, so the trig pin high. Oh, and another thing, be very careful when you do wire this TIVA-C with the distance sensor, that you don't wire it to the wrong place. Because this is actually my second TIVA-C, and the first time I killed it was doing literally the same thing. I just connected the ground pin somewhere else and just killed the data bus. So you don't want to have that happen. Digital right. Okay, so now we go delay microseconds, right? So in here, this is however long you want the period to be, essentially, because you want, so this is this part. So if you can think in terms of the timing diagram now, after you write the digital right, trig pin high, think like you're on a graph, you go up now, right? Like the signal's up. This is the positive rising edge. Now you're here, now you're on the little flat line, the zero slope area. So the delay microseconds now just means how long do you want that line to stay high? So how long do you want the graph to go straight in a zero plane? Okay, right now I'm explaining as if I have it pictured, which I have. I'm hoping you do too. So you can say 100 microseconds or 1,000 microseconds. Just make it long enough so that you can work with it, so that and also that microcontroller can work with it. I have 1,000 microseconds, which is like 1,000 microseconds. Yes. 1 second, if I'm not mistaken. In any case, that's fine. 1,000 microseconds is good enough. All right, and then now we have to basically bring the signal back down, because you're basically creating a cycle. You're creating a pulse, right? And remember from the data sheet, we said that we need at least a pulse of 10 microseconds or more. This is 1,000 microseconds, so which is like 1 millisecond or something. I think I might be mistaken. I think just don't quote me on that. I haven't done the math.
That's you.
Okay, so digital right, straight pin. We want this to be low. Okay. And so now we want the duration, right? Duration, DUR. You can call it time elapsed too. It's going to be pulse in. So this pulse in is a built-in function that literally just listens to pulses, and it also times the pulses actually from the listening. Oh, let me try to remember. Because I Googled it once. It's also in Arduino as well. What it listens to is what you pass it in, right? So for example, like what we're going to pass now is echo pin. That's parameter 1, and the second parameter is high. So now it will just basically listen to the high pulse. It will time it from the first to the second, and then just give you the delta. And that's basically what we want. And if this was in Code Composer, what you would have to do is you would have to configure the built-in timers as a half-width timers, and then start the clock basically when you first send the high pulse, and they capture that time, and then start basically capture the time another time when you have the another high edge, and then divide it. Then subtract time. It's just basically more code, does the same thing. Okay, and you want a delay here because you want to give it some time to make the measurements. And also, the longer the delay here in this line of code is, right here, the longer the wait there is before it is printed out to your comp, yeah, your comp port, your UART, quote unquote, right? The serial monitor, at least in this thing. Okay, so it's really up to you. I'm gonna put this in 1,000 so that it's somewhat seeable. Okay. And you can put this delay after you find the distance, so that's fine.
Sorry.
Oh, no, that's fine. Okay, and in any case, it's fine. Distance. So now we have distance, DST, duration, which is dur, and we're dividing that by 54. That's 54. At least the way I had my code earlier, I done 29 and then divide that by 2 again, which is the same thing as saying 29 times 2, which is 9 times 2 is 18. Yeah, it's 58 actually, not 54. My apologies. Just do 58. You're also able to find resources on like specific how to work with this um uh, this distance sensor and on the TIVA-C online as well. Because there's actually quite a bit of work on this. And they also just use this Energia IDE, or they use Q. Very few people use Code Composer, which is one of the reasons of difficulties when you work with Code Composer. It's because there's very little support for that. But our professors would like to use Code Composer because it helps you sort of work with APIs, right? Because with Q you're working with C, but then you're talking to a resistor or a register all the time. With Code Composer, you're just using API functions that just take care of the whole thing. So it's like it's easier in that front, but you really don't know what's happening down in the cellular level of the microcontroller. Okay, so that's the distance, and then now we just want to print the distance. Okay, and the way we do is serial.print. And the reason we have serial here is because the communication most supported by the TIVA-C is the serial communication. So UR is also serial, and serial just means in sequence. Okay, that's all that means. So distance. Okay, we'll just do something like this. Then we do serial.print again. And the good thing about here is that I don't have to worry about the buffer, the message buffer. In other modes, you do have to worry about the message buffer, right? Like how big do you want things to be? Over here, it just does it for you. Distance. And because this is in centimeters here, according to the data sheet, we're going to say centimeters. If you want to put it in inches, you divide by 148. That gives you in inches. Okay. So what I'm going to do here is I'm going to print again. Serial.print centimeters, right? Actually, I might also just show the value in inches as well. So the way I'll do that is serial.print dur, divide that by one, how much was it? 148. Now, one bad thing about this IDE is that if it breaks up. You gotta restart the computer. Because you're not able to close it. I tried. I wasn't able to close it. So that was that. And let me add some space here, a couple of spaces, actually 2 spaces. And serial.print inches. I think inches is IN, I believe. Right?
Yeah, I had.
Okay.
You got it right.
Can't believe this. Look, college about to graduate, don't know how to imagine inches.
Damn imperial words.
Yeah, I know. Don't say. Okay, so now I'm gonna stop share, and I'm gonna share the entire screen so that they can see the components. All right, we'll share the entire screen here so that you can see everything. Now let us compile. Low was not declared, so we messed up somewhere. Where do we mess up? Oh, right here, because it's not in capital. Okay. So we're compiled, we're good to go. The moment of truth. Oh, and let me see. Let me also open the COM port, which is a serial monitor. So this is called a serial monitor. If you're using UART by itself, I think you would just call it comp. I'm not even sure what you call it. I think you would still call it a serial monitor. Just call it a serial monitor. We're good. And then upload. There you go. We see a success, and let's see if there's anything. Oh, 0.0. Okay, there's nothing. So okay, oh, that's the reason is 0.0 is because our plus wire, our red wire for the power supply is not connected. So it's not good.
Do we
There we
need to
go.
put some object?
Well, yeah, it's
Leave it
reading
in
it.
your
It reads it for. So you can see it's 10 centimeters. So whatever's in front of me right now, it's actually, I think it's reading the plastic. Probably it's 10. It's 9. Now it's closest. Yeah, now it's 5 centimeters and all that. So yeah. Also, it's slow because of the delay, right? So if, let's say I put 100 here, it's gonna go by very quickly. Clear this look. So it's really how big the delay do you want it to be, and I think we would have to put 1,000 here. Let me put 10,000 and upload. Okay. So now I'm gonna clear, and then you can actually see it come. So just hold on. It's on delay right now because I just cleared it. There we go. So 9 centimeters and then 3 inches, 6 centimeters, 2 inches. Like, of course, I'm pretty sure there's some white values here, which means white error values. But and then the way you would work with that is I think you would actually have to do empirical measurements. So for Dr. Lay's class, when I worked with an IR sensor, what we had one of my teammates did is after the ADC values are configured, which is there's a formula for that, the actual accuracy you have to determine via empirical values. So like there may be a few things that you have to subtract or maybe add, but for sure there's obviously going to be errors, right? Because these are cheap things. They're not actually super sensitive. And also another bad thing about this one would be that it's an ultrasonic wave. So and if it gets knocked into if it knocks into anything really, like you could probably not see it, but because the wave is small enough, it can just come back, and then like that noise can be added to. So there's definitely issues there. But yeah, that's really it, and this code will be in the repo.
Do you want to show just a little bit? I'm going to switch cameras.
Yeah, okay, I can show.
So you can show the board.
Yes.
And anything else. I'll just leave the camera there.
Okay, which board? Which board do you want?
You can show the TIVA, maybe again how you wired it.
Oh, okay. So, actually, I don't have to have it working for that, do I? So, this green wire is the ground, right? I'm using a female to male wire, so there's a G and E right here. If you look so if you look in the wordings of all of these little words here, these little words here that go vertical, and they're the pin names, right? And you have respective pin names on the back as well. So if you only have male to male wires, just use this side. I happen to have female to male conversion, so we're good here.
If you only have male to male wires, it's pretty good.
Anyway, your way is just not interested. We're good. Anyway, you have ground, so I'm using ground. Ground is this one, because over here you see PF2 and GND, right? PF2 is the left one side, GND is the right. So this is the ground that connects to, again, the minus of this board, the gray wire. You have to connect this here because there's circuitry inside the board too. So if you don't ground it together, if the ground isn't shared, then like the sensor and also the TIVA doesn't really know where the measurement's happening, on what basis. So that's basic circuitry. You have to have that. And then PC4 is this green one. I'm sorry, not green, this brown. This is the trigger pin, right? It's connected straight to the trigger pin on, this is the yellow one. It's connected to the trigger pin here. I can't really see it well, but that's the trigger pin. And the white one is the echo. Echo is the one that listens to the echo of the wave. And the reason it's called echo is because it quite literally is an echo. uh, I'm using word to define a word here, but what I mean is, so when I'm talking, you know how the sound, whenever you hear an actual echo, what really happens is you have your sound waves, but then they collide, and then they come back to you, and then while they're coming back, it's making noise. And ultrasonic is the same way, like how bats use their ultrasonic. You know how when bats move, they make their sound a lot. So what they're really doing is they're sending those high pitched noises from their mouth, and then they listen to the ears for their reflection or the echo, and depending on the distance, then that's how they figure out the distance. So that's basically what this thing is doing. It's just when I listen on the code, what we're doing is we're listening to the high pulse, and the timing delay there. It's going to be the one. The total time there is going to be the total width, and then you divide that by 58 or 100 something. I forget, which is on the data sheet. That gives you the time centimeters or inches, and that's really it. And after that, you just if you use centimeters, you want to find that in meters, just use your conversions, and you're good to go. Also, you're free to use any of the pins, but you don't have to use the pins I use.
Show the pins on this. Like actually take it out.
Oh yes, I can do that. So here, let's look at the pin values here.
Probably not going to focus, but I'll have to take a picture of it. Yeah, it's.
Oh,
Oh, there it goes.
There you go. So you have ground, echo, trigger, VCC, right? VCC is the. I'm sorry, this is actually reversed. So I'm using my left hand. Looks like I'm using the right hand. Oh my goodness, my fingers are dirty. But anyway, VCC here is the voltage, right? Voltage source. That's the 5 volt that it needs. Ground is the ground. Also, ground doesn't actually have to be 0 volts. You can actually have it to be 10. I mean, less than VCC, right? You can have it 3 volts, but just make sure the TIVA-C also has that 3 volts grounded. That's the beauty of ground. It's really the whole thing about voltage is just potential difference. That's literally what voltage is. So if your difference, as long as you can maintain that difference, doesn't really matter what the ground is. And echo and trigger respective pins. Echo is the one that listens to the signals. Trigger is the one that outputs. So whenever you output a wave to trigger, what happens from this? Outputs the wave, and then it listens to the. You have sensors here actually on the side, here and here, and like in the middle. You have sensors here. Not exactly not too well, but you do have sensors here. But yeah, it's relatively simple to use. When you compare it to an IR sensor, it's just harder to use when you use the sort of IDEs we use in professional development. This works well for your DIY projects or with Arduinos, right? Actually works well with that, and that's probably why I bought it. It's just with the TIVA-C, and you try to use Code Composer, it's sort of hard. Keel, if you want to use this with Keel, you just don't even have to Google. You just have to just say, hey, using HC-SR04 with TIVA, and then there's a little article that just takes you step by step on how to use Keel. Because Keel is still talking to register, and it's easy to configure the timers with Keel because the data sheet helps you. And with the data sheet, if you just follow that in Keel, you got it, right? It's just with Code Composer, you don't get to do that. At least I'm not aware of it. You only use APIs, and the APIs are sort of tricky, and then it gets into a lot of extra details. I tried 2 days. I wasn't able to do it. But yeah, have a good day, y'all.
Let me just say something real quick. So.
Thanks everybody for joining. This concludes our session 3 of TIVA-C functionality. Thanks again, Tabi Cadell. Have a good day.